Everyone's talking about trillion-dollar AI data centers relying on nuclear power plants to run. But what if we built one for a tiny Eastern European village? In this video, I'll be explaining how AI data centers work to Mike Babushka, who still thinks Facebook is the internet. The functionality of AI data centers can be split into four basics: compute, the connectivity, the cooling, and the power. We're going to dissect each one of these parts in its individual components. I will explain to you how all the different parts function in the modern day. Then we're going to scale everything down and fit it in our Eastern European village data center. So, compute. AI data centers exist to perform massive amounts of math, mostly matrix multiplications, for the purposes of training and running AI models. The brains of the AI data center is the GPU and its friends. The heavy lifting is done by GPUs, also called graphics processing units, or newer AI accelerators like TPUs, which Google has been producing, although they are still not in massive use. Each chip contains thousands of small cores that can run simple calculations in parallel. This is perfect for neural networks, which AI models are. A typical AI GPU, like NVIDIA's A100, can deliver tens of teraflops or trillions of operations per second. AI data centers are like hives for so-called nodes, the servers for AI. Each node is a server packed with multiple GPUs, often between 4 to 8, and they are connected to high-end CPUs, and they have huge allocations of RAM. You can think of hundreds of gigabytes of RAM, and they have access to fast local storage like NVMe SSDs. Now, each node is part of a cluster. One cluster contains thousands of these nodes connected via ultra-fast networks like InfiniBand or 400G Ethernet. The network fabric is key. It lets the GPUs across different servers act like one giant computer, where the collective acts as the training cluster. Next, we get to the storage layer. AI training consumes and produces petabytes of data. Fast distributed storage systems, for example, Ceph, Lustra, etc., feed the GPUs with training data continuously. Latency here is critical, and GPUs sitting idle cost millions. The software stack consists of training frameworks like PyTorch, TensorFlow, JAX. Each one of these guys split work across GPUs automatically. The orchestration most often happens through Kubernetes, which is used to schedule jobs on thousands of nodes. And the libraries used are often CUDA or NCCL or MPI, which handle the low-level parallelism and GPU-to-GPU communications. The two main workloads are training and inference. Training, on one hand, is used to build new AI models, which rely on huge clusters for weeks and months, operating constantly 24/7. And once a run is started, it is not stopped. It is difficult to evaluate how accurate the results are going to be or how much better is it going to perform than previous iterations. Training is extremely costly, and the primary reason why companies like OpenAI are constantly raising billions and billions of dollars. Inference, on the other hand, runs these models and is the main way AI companies generate their revenue. These workloads are smaller, latency sensitive, and way more distributed. Finally, we get to the question of why all of this is so power hungry. Well, each GPU can draw between 700 to 1000 watts, multiplied by tens of thousands, add cooling, networking, etc., and you start looking at hundreds of megawatts. This is where the AI data center needs its own power plant narrative comes from in the general news. In short, AI data centers are giant math factories. Thousands of GPUs exchange answers over ultra-fast networks and keep doing that 24/7 until a model like ChatGPT or Stable Diffusion is born. And then that model is spread across different AI data centers and made available to the general public through the chat interface or similar tools. Connectivity. The goal is obviously to connect everything. Servers to each other, servers to storage, and the servers to the outside world with as little delay and as much bandwidth as possible. Most AI traffic happens inside the data center. GPUs constantly exchange data during training. These connections are called east-west connections. Server to server, not server to the internet. Most AI traffic happens inside the data center. GPUs constantly exchange data during training. These are called east-west connections. Server to server, not server to internet. AI workloads need microsecond level latency and terabits of bandwidth. The fabric layer, or you can imagine it as the nervous system of AI data centers, built with high-speed switches and optical links, each one having between 400 and 800 gigabits per second per port. So you can imagine how this is going to multiply quite rapidly. The common tech used for these is InfiniBand, which is an NVIDIA solution. It is ultra-low latency, purpose-built for HPC and AI clusters. Also, Ethernet is used. It has similar speeds but is cheaper and more standardized, thus the more common solution. The network interface cards are mounted on each server, oftentimes multiple per server. Even more often, they're built into the GPUs themselves, hence the NVLink plus network interface card combo, the high reliance on NVLink for communication purposes. These guys handle packet transfers, offload CPU work, and sometimes compress data in flight. High-speed storage systems connect via the same fabric or a parallel one. Technologies like RDMA let GPUs read data directly from storage over the network, no CPU required. External connectivity, i.e. north-south traffic, is handled through data centers which are connected to the wider world via multiple tier 1 ISPs or cloud backbones. These links are typically 100 to 400 gigabits per second per link, often in redundant pairs for reliability. Edge routers include BGP peering, load balancing, firewalls, and NAT gateways. All paths are redundant, N+1 or better, meaning that any cable or switch can fail without downtime. The automatic routing protocols reroute traffic in milliseconds as well. AI clusters depend on precise timing between nodes. A lag of milliseconds can desync training. Technologies like precision time protocol or grandmaster clocks keep all nodes synchronized down to the millisecond. Lastly, in terms of power and optics, the optical fiber dominates. Copper can't handle long runs at 400 plus gigabytes per second. Transceivers, multiplexers, and dense cabling trays manage thousands of fiber links. Data centers often have tens of thousands of fibers weaving through the racks like neurosynapses. In short, connectivity is the AI data center's nervous system. It links tens of thousands of GPUs so they can think as one, moving terabytes per second with almost zero delay. Without that invisible web of light, all of those metal brains would just sit there thinking alone. Next, let's discuss cooling. The point of cooling is quite obvious. It is to keep thousands of GPUs and CPUs from overheating while using the least energy and water possible, because every watt of compute becomes a watt of heat. The problem we're trying to solve is that there is heat everywhere in these buildings. GPUs convert almost all electrical power into heat. A small AI cluster gives off as much heat as 8 to 10 space heaters running non-stop. Without cooling, components would throttle or fail in seconds. The basic idea of cooling is that cooling is just heat transfer. Move heat from chips to air or liquid to the outdoors. AI data centers focus on doing this efficiently because cooling can consume up to 30 to 40% of total power if done badly. The main cooling methods used today are air cooling, which is the traditional way of cooling. We just blow cold air through the servers and exhaust the hot air out. Cold and hot aisles are separated to avoid mixing, and this works for 10 to 15 kilowatt per rack before inefficiency skyrockets. Fine for small labs, but not for dense AI clusters. The modern AI standard is liquid cooling though. It moves heat with water or dielectric fluids directly from components. There's a few ways that liquid cooling works: through cold plates, where water channels sit directly on GPUs or CPUs, and the heat flows from the chips to the copper plate to the circulating coolant. The warm coolant leaves the rack, passes through a heat exchanger, and dumps heat outside via chillers or dry coolers. There's another variation of these called rear door heat exchangers, where cold water runs through a radiator on the back of the rack and it captures the hot exhaust air before it enters the room. And the last option is called immersion cooling, which does, as it says on the tin, servers submerged in a non-conductive fluid bath. Fluid circulates through an external cooling loop. This solution is ultra efficient and silent and is used for very, very dense setups or remote setups. The cooling loop has 4 different steps. Inside of the loop, where water carries heat from chips to a plate radiator, onto the heat exchanger, where heat is transferred to an outside loop, then outside of the loop, where chillers, dry coolers, cooling towers, etc. release the heat to the environment, and lastly, pumps which keep everything flowing at a few gallons per minute per rack. There are different cooling options depending on the climate. For cold climates, we have the so-called free cooling, literally just run the fans. No chillers needed for most of the year. For moderate climates, we have dry coolers with adiabatic spray or hot days. And for hot or humid climates, we have chillers or hybrid systems which consume way more energy. In short, cooling is the lifeblood of an AI data center. It is necessary for day-to-day operations, but is different between each one. Next up, power. The goal of this component is obviously to feed enormous, always-on machines with constant, clean, redundant electricity, because even 1 second outage can crash weeks of AI training and lose the company millions, if not billions of dollars. The power demand of AI data centers is massive, often 30 to 300 megawatts, which is equivalent to a small town. A single rack of GPUs can use 40 to 80 kilowatts, which can be multiplied by thousands of racks. Power is the #1 limiting factor in where and how fast these can be built. This is why the power source matters. AI data centers are connected directly to high voltage transmission lines, 110 kilovolts or higher. This is an example of a 100 kilovolt or higher power line, just if you didn't know what it means. High voltage power from the grid enters through transformers stepped down to medium voltage, around 14 kilovolts. Of course, we also have backup power. Between the grid and the servers sit uninterruptible power supplies, big battery banks. Between the grid and the servers, we also have UPS systems, uninterruptible power supplies. You can imagine big battery banks. They cover the few seconds between a grid outage and the startup of a diesel generator. Each UPS is redundant, n+1 or n×2, and it is constantly tested. So the generators, rows of diesel or gas generators that stand by outside the building. They can keep the facility running for hours or days depending on the fuel storage, and they have an auto start and sync system with the UPS within a few seconds of power loss. A perfect data center would have a PUE, or power usage effectiveness metric, of 1.0. But traditional centers often hover around 1.4, and the more optimized ones between 1.1 and 1.2. Why AI makes everything harder? GPUs still pull power in sudden surges, aka burst loads. Power systems must absorb those fluctuations without voltage drops, and dense AI racks can exceed cooling limits, forcing higher PUE or liquid cooling. Everything in these systems is tracked: voltage, current, temperature, and there are real-time alarms tied to all of this. Automatic load balancing keeps critical paths stable if one feed fails. As I mentioned earlier, the cost of a failure or an outage is multiple times the cost of having backup ready and running. There are many challenges associated with setting up a data center. One of the big ones is the grid connection delay. This requires multiple years of approval due to the amount of strain that it puts on the system. Also, there is local opposition due to noise, emissions, and grid strain. If you want more details on this, by the way, have a look at Data Center Valley in North Virginia. There are multiple interviews with the locals that report absurd amount of noise, often leading people to sleepless nights and, frankly, just insanity. In short, power is the lifeblood of an AI data center. Electricity flows from high voltage lines through layers of transformers, batteries, generators, everything feeding thousands of GPUs that never sleep. One flicker and the entire artificial brain forgets what it was thinking. And then goodbye, millions. So, what if we built one ourselves? We're going to assume that our village has around 1,000 people, which would look like this, and we're going to work off of the assumption that at most 10% of people are going to use it on average. We're going to target around 20 requests per second, which is going to require around 5 NVIDIA A100 GPUs. The per server power draw is going to be around 2.8 to 3.8 kilowatts. When multiplied by 5, for redundancy, this will be a total of just under 20 kilowatts of power draw. For cooling, we're going to end up using, I don't know, man, this kind of a pump, which is a 7 GPM pump to offset enough heat from these GPUs. Simply put, this server is going to fit in somebody's garage. It is not large at all, which should really put it into perspective compared to the large centers that are being built, which of course are meant to power millions of people and probably millions of requests per second. It's actual insanity. The storage and networking speeds here are negligible. We could make use of 100 gigabit connections and will be more than fine for internal transfers, and then maybe 20 gigabits for external transfers. The total cost per year that we're looking at is maybe around 100 megawatt hours. The cost to operate this would be between 10 to 20k, and the emissions are between 10 and 60 tons of CO2. On the other hand, the village would end up getting a lot of different jobs for operators, cleaners, maintainers, builders, etc., which does have its benefits. At this kind of scale, we're not looking at a huge noise pollution or emissions pollution. Of course, if we would build this for the scale of Bulgaria, the power grid is going to get browned out every couple of hours due to use. This is why these centers are generally built in clusters which are specifically made to support them, and then access to them made available through data centers across the world. If this video was helpful to you, please like and subscribe. If you have any feedback for me, leave it in the comments. Thank you so much and have a wonderful day. Goodbye.